So today we are going to start a new topic, current electricity. So we all are aware of uses of electricity. So electricity is one of the most important blessing that science has given to the mankind, and we are so dependent on electricity that today we cannot imagine our life without electricity. So out of so many uses, like sitting in a room, you turn on AC, and with this hot weather you can make yourself comfortable, and when you want to travel from one part of the city to another part of city, you use metro. So there are so many things which are dependent on electricity. So it is the most important topic. Every year like 2-3 question comes in JEE from electricity. So today we will see this topic. So our modern home appliances, our mode of transport, everything depends on electricity, right? So before we get into electricity, we will first talk about the type of material we are having based on whether they conduct electricity or they do not conduct electricity. So first one is conductors. Those material which freely allow charge to flow are called conductors. Now most of the metals are good conductors, they easily conduct electricity. So if I take one example, let us take any metal, for example copper. If I take, now copper, around nucleus electron will be revolving, and if you look at the outermost electron, it is less tightly bounded to the nucleus and it is free to move. With a small amount of energy, it will come out of the influence of this nucleus and free to move. So if I take a small part of the copper block, inside that what will happen, those loosely bound electron, they can easily move and they can come in the influence of another nucleus, right. So as you can see that this was revolving here and then it moves to another atom. So this way electron can freely move inside conductor, because outermost shell electron, they are lightly bounded. With a small energy, they can easily come out of the influence of the nucleus. Then comes insulator, which do not allow electricity to flow through it. So there in the outermost orbit, the electrons are tightly bound, and with the normal electric field or under normal circumstances, they cannot get free from the nucleus. As they cannot get free from the nucleus, they cannot roam through insulator, right. So you can see the definition. An insulator, in an insulator the electrons are bounded rather tightly to the atoms and they are not free to move. Under normal circumstances. So examples, plastic, ceramics. So you must have observed that when you must have seen high tension wires, they are attached with a ceramic ball which is holding the wire, and that makes that electricity not to come through the pole, right. So we are using insulator there so that there is no conduction between the wire and the pole. So ceramic, as it is insulator, it won't allow electricity to pass, right. Apart from these two, conductor and insulator, there is some material which is in between these two, right. So what are those material? Those are called semiconductors. So semiconductors are those material in which very few electron will contribute to the conduction. So, how many such electrons? In 10 to the power 10 to 10 to the power 12, there might be only one atom which will be giving electron so that electricity can flow. So, those type of materials are called semiconductor. They are intermediates between insulator and conductor, right. For example, silicon, germanium, these are the material which comes in this category. They are called semiconductor. How their energy levels getting affected, and what is the role of energy level in their conduction, that we will see later. But for time being, we are just talking about the material which can freely conduct and the material which do not conduct at all. So, in this chapter we are not talking about the semiconductor. Later we will talk about semiconductor in detail, right. So, these are three basic type of material. There is one particular condition in which a good conductor start behaving as superconductor. So, all the metals which we are using, those are conductor, but even then they offer some resistance to the flow of charge. So, as they offer resistance to the flow of charge, now while passing through the medium or passing through material, electron start striking the atoms and it is not that free to move, right. It is observed that when we decrease the temperature of those material drastically, the resistance offered by the material decreases, and in that situation those materials are called superconductor. So, last one is superconductor. So, even best possible conductor like copper, silver and gold, they show some non-zero resistance to the flow of charge carriers, and when we decrease the temperature, the resistance they are offering gets drastically decreased, and at that time those material are called superconductor, and this ability is called superconductivity, right. Now, we talk about the material. Now, we will talk about what is current. What is electric current? It is rate flow of charge through a given cross section. With what rate charge is flowing through a given cross section, that measurement is called current, right. So, electric current through an area is the rate of transfer of the charge from one side of that imaginary area to other side, right. So, let us see one animation. As you can see, charge particles are moving through material. If I take imaginary area over here, so charges are passing this imaginary area. With what rate they are crossing this imaginary area is called electric current. So, if I want to find out current, then what I need to do, I will calculate how much charge is crossing through this area in dt time, total charge that passes through this area in dt time, divide by time will give me current. So, this will give me average current. So, this is average current. And this is the total charge that crossing the area, and this dt is time interval. So, this is over the period how much amount of charge cross the area, divide by period will give you on an average current. But if I am interested in calculating or finding instantaneous current, for example, at this particular moment what is the current at this particular moment, for example, at t is equal to 1 second, t is equal to 2 seconds, if I am interested in calculating current, so what I can do, I can reduce the duration, and if I make delta t tending to 0, then this whole value will become instantaneous value. So, this can be written this way: limit delta t tending to 0, delta q by delta t, this whole expression will become dq by dt, and this will give you instantaneous current. So, to calculate instantaneous current, I need to differentiate charge with respect to time, and to calculate average current, I need to calculate total charge and divide by total interval, I will get average. So, these two formula we will be using to find current in the given situation, right. So, let us talk some properties of this current. So, we are defining new parameter called current. Let us talk about property of this current. Now, the particle or charge what we are talking about can be only electron, can be only ion, or can be the combination of electron and ion. And later we will learn that in semiconductor, in absence of electron is defined as hole. So, there we will consider movement of electron and hole, but right now we are not talking about the semiconductor, we are just talking about normal materials, conductors, right. So, in that situation, how the current will be flowing, you can see the moving particles are called charge carrier, right. And in different conductor there might be different type of charge carrier. So, if I just talk about copper wire, so through copper wire electron will be moving, so charge carrier in copper wire will be electron. If I talk about cell, so inside electrolyte there will be movement of ions. So, in electrolyte, in normal circuit it is a movement of electron, right. In electrolyte in the cell there will be movement of ions, so charge carrier will be ions in that situation. While in ionized gas or plasma, charge carriers are ions and electrons, right. So, if I take normal circuit, look at this one. So, we have got one battery and conducting wires which is connected to bulb, right. So, when switch is closed, there is a movement of electron. Electron moves from negative terminal of the battery to positive terminal of battery through external circuit. So, from negative terminal electrons are coming out, flowing through the circuit and entering back to the positive terminal of battery. So, this is the direction of flow of electron. By convention we defined the direction of current opposite to the direction of flow of electron. So, electrons are flowing in this direction and we say current is flowing opposite to the flow of electron, right. Inside this conductor there is movement of electron only, but if we talk about the battery, inside this cell there is a movement of ion. So, inside the cell there is movement of ion, charge carrier will be ion, but here on this conductor there is movement of electron. So, here charge carriers are electron, here charge carriers are electron, and here charge carriers are ions, right. So, when we are defining a physical quantity, we require a unit to measure it. So, what is the unit of measuring current? It is ampere. So, current is measured in ampere. For example, in circuit we say that 2 ampere current is flowing, 3 ampere current is flowing. So, it is represented by 2A, or this way also it is written, right. So, current is measured in ampere, SI unit of current is ampere. Next point, current is a scalar quantity. though we are representing the direction of flow of current, as it is not following vector law, it is a scalar quantity. Here the arrow, the direction of arrow is just, you can see here, the current arrow shows only the direction of flow in the conductor, not in space. So this arrow is for the idea that in what direction charged particle will be flowing. I can say that electrons are moving in this direction, these negative charge particle moving in this direction, or I can say the positive charge moves this way, right. So generally we draw it this way, but actually there is no movement of positive charge particle. Nucleus inside the conductor remains stationary, the whole atom will be vibrating because of thermal agitation at their mean position or about their mean position, but they cannot move. So positive charge particle won't be moving, but generally for normal representation we draw it this way also, right. So this current is just representing the direction of, I can say, direction of movement of positive charge, or the direction of current is opposite to the direction of movement of electron. So here arrow is just indicating in what direction these charged particles are moving. It has nothing to do with the direction in space, as it is not following vector law, it is a scalar quantity. So current is a scalar quantity, right. Now, so I hope definition is clear. The instantaneous current is given by dq by dt, rate of flow of charge, rate of flow of charge. And if you are interested in calculating the average value, then calculate total charge divide by total interval, then you will get average value. This is what we have learned. And we have also learned that there might be different charge carriers. It might be only electron, it might be only ion, or it might be combination. And the last point, current is a scalar quantity. Now, using all this we will see some numerical. So first one is 10 to the power 6 positrons are flowing normally through an area in forward direction. And the same amount of electrons flowing backward for interval 10 millisecond, not 10 to the power 10 millisecond. What is the current through the area? We need to find out current. What are positron? For electron we have charge on electron 1.6 into 10 to the power minus 19. Positron are the particle having same amount of positive charge and same amount of positive charge, and the mass of electron is same as mass of positron. So positron are the particle having same charge as that of electron with positive sign. Here the charge on electron minus. So if I want to write charge on electron, I will write minus 1.6 into 10 to the power minus 19, while for positron I will write charge 1.6 into 10 to the power minus 19, right. So I hope it is clear. So if positron is moving in forward direction, look at this one, positrons are moving in forward direction, and this will make current due to movement of positron in this direction. Along the direction of motion of positive charge there will be current, and at the same time electrons, which are oppositely charged particle, moving in opposite direction, right. So moving in opposite direction. So as negative charge is moving in this direction, because of the movement of negative charge, current will be in this direction. So, current because of positron in this direction, current because of electron in this direction. If I ask how much charge has flown through this area, how much charge has flown through this area? So, charge will be equal to number into charge on electron, and electron and positron both are having same charge. So, this is due to the movement of electron and this is movement of positron, both are having same charge. I can multiply this to 2, right. So, if I get the total charge, this will be total charge, right, total charge that has flown through this imaginary area. If I divide it by time, then I will get the value of current. So, what I can write, I is equal to q by t, where q is this value of q I can substitute over here, and this will become what? As you can see here, this is 10 to the power 6, and the charge on electron 1.6 into 10 to the power minus 19 into 2. If you simplify, this will become 3.2 into 10 to the power minus 19. Divide by time interval, what is given, that is 10 millisecond. So, what you will get after simplifying is 3.2 into 10 to the power minus 11 ampere. Generally in the previous case, I told you 2 ampere current flows or 1 ampere current flows. These 1 ampere, 2 ampere currents are very large currents, right. So, generally the range of current what we get at our home, that is somewhere around microampere or milliampere, right. Milliampere is also large current. So, current in ampere, 1 ampere, 2 ampere, that current is very large. So, generally range will be small, okay. So, this is the way we can calculate current. So, charge particles given, positron as well as electron, positron positive charge particle, I can consider current due to positive charge particle in the same direction, and current due to electron, as electrons are moving in opposite direction, you can see the current will be in forward direction. So, adding these two, I will get the total current 3.2 into 10 to the power minus 11, right. Now, let us see another example. What would be the number of electron passing through heater wire in 1 minute? If it carries current of 8 ampere, so 8 ampere current, obviously very large current. Let us see how many electron must have passed through the wire to have 8 ampere current. So, again formula is I is equal to dq by dt. dq I can write n into E divided by time, right, this way. So, this expression can be written this way, n number, E charge on electron divided by time. Here I require number, right, n I require, current is given 8 ampere. So, I can substitute value here. First simplify, I into T divided by E will give you number, right. So, after simplifying this one, I am getting 3 into 10 to the power 21 electrons. So, these many electrons crossing the wire in 1 minute will make 8 ampere current, okay, which is very large current, right. Now, let us see another example. Charge through a cross section of the conductor is given by, so this is the way charge is given, 2t square plus 5t coulomb. Find the current through the conductor at t is equal to 2 seconds. So, charge is given and you need to find out current at t is equal to 2 seconds. So, formula is I is equal to dq by dt, right, to calculate instantaneous current. So, to calculate instantaneous current, what I can do, we can differentiate this charge. So, differentiating this charge will give me what? Here 2t square differentiation. So, 2t square differentiation will give you 2t plus the differentiation of second term, that will give you 5. So, current through the wire will be 4t plus 5, and you are asked to find out current at t is equal to 2 seconds. So, substituting 2 second here. So, what we are getting, I is equal to 4 into 2 will give you 8 plus 5, that means 13 ampere current will pass through the wire at t is equal to 2 seconds. As you are getting current as a function of time, that means at different moment current through wire is different. Now, in the previous case, this was a constant current flowing through the wire. So, current through the wire is always 8 ampere, while in this situation you can see that current through wire changes with time. At different moment the current will be different. If I ask what is the current at t is equal to 1 second, so if you substitute t is equal to 1 second, then you are getting only 9 ampere current, right. So, current keep on increasing as time increases, current increases. This is the expression, as time increases current through wire also increases, okay. So, this is the example of varying current, previous was the example of constant current. Now, let us see another example. So, again here you can see that current is varying with time. Previous case it was linearly varying, look at this one. Previous case it was linearly varying, I to the power 1, t to the power 1. Now, here non-linear variation is given, I to the power 1 and t square. Here question is different. So, the current in the wire varies with time, current is given. How many coulomb of charge pass a cross section of the wire in time interval from 0 to 10 second. From 0 to 10 second, how much charge will pass through the wire, right. So, current given, charge is asked. Previous case charge was given, current was asked. So, I is equal to dq by dt, right. So, if charge is given and current is asked, you differentiate with time, you will get current. But if current is given and charge is asked, you can integrate this expression. This way you can write dq is equal to I dt. So, if I integrate, I will get the value of charge, total charge that has flown through the wire. So, current I can substitute here. So, let us substitute and simplify. Let us first generalize the expression. So, from 0 to t second, how much charge has crossed the imaginary area? So, this if I simplify, look at this term, dt if I get in, then this can be written to integration dt plus this is 0.6 t square dt limit 0 to t. So, this q after integration is coming 2t plus t cube by 3, 0.3 t cube, right. Here you will get, sorry, 0.2 not 0.3. Okay, now, so this is the way charge flowing through cross section varies with time. and you are asked to find out that up to 10 second how much charge has flown. So, I will substitute t is equal to 10 second over here. So, 2 into 10 plus 0.2 into 10 to the power 3. So, 20 I can see here, 200 I can see here. So, this much charge have flown through the cross section. Similarly, I can ask from t is equal to 1 second to t is equal to 4 second how much charge is flowing. So, only thing I need to do is just change the limit from t is equal to 1 second to t is equal to 4 second, 1 second to 4 second, then you will get in that interval how much charge has flown through cross section, right. Charge is given, current is asked, differentiate. Current is given, charge is asked, integrate, right. So, this is what we have done. Now, let us see another example. So, total charge passing through wire till t is equal to 6 second varies with time. This plot is given, current is a function of time. Right. So, this variation is non-uniform because you can see that t is equal to 0, current is 0, up to 2 second it increases to 4 ampere, then it remain constant up to 5 second and that reduces to 0 at t is equal to 6 second, right. Question is find the total charge passing through wire till 6 second. So, current plot is given and charge is asked. As we know that I is equal to dq by dt, that dq can be written I dt as this is in the form of y dx. I is plotted on y axis and x axis we have time, right. So, this is in this form. The physical significance of this is area under curve and x axis. So, this one is area under curve and x axis. That means to get this quantity I need to get the area under current and time curve. So, area under current and time, area under curve and time axis will give me charge. To calculate charge I require this area. This total area I require to calculate the charge flown up to t is equal to 6 second. So, let us find out area. So, you can see this triangle. What is the area of triangle? Half base into height, half base into height, this over. Now, look at this part, rectangle. So, this gap is 3 and this height is 4. So, area will be 3 into 4 plus, again I can see triangle, half base into height, half base 1, height 4. So, half base into height, half 1 into 4, okay. That is the total charge that has flown. If we simplify, I can see 4 here, 4, 12 and then this and this will get cancelled out. Here 4 and this is 12, 4, 12, 16 and this will make it 18. So, 18 coulomb charge flows through the wire up to 6 second. In the same situation if I ask like till t is equal to 4 seconds, how much is the charge flowing, right? I have taken some intermediate value of time till that I am asking. So, we will consider the area up to that. So, 4 second will be somewhere here, 4 second will be somewhere here. That means I need area only up to here, to calculate charge up to 4 second. So, what I need to do, I am solving V part now, second part, up to 4 second, up to here only I need area. So, triangle area half base into height we have already written, and then we will write this area, this is 2 second and this is 4 second, 2 into 4. If I simplify, 4 I can see here and 8 I can see, so 12 coulomb. So, up to 6 second you are getting answer 18, and here we are getting answer 12 coulomb, right? Okay. In the same question, if I ask what is the average current up to 6 second, so let us add one more part, find average current from t is equal to 0 to t is equal to 6 second, then what we need to do. So, what is the on and average current flowing through wire, how to calculate that? See, so to calculate average, we can use the formula what we have started with, average, current average is total charge flown divided by the interval. So, if I want average current, then I need to write charge here, right? So, charge here is 18 coulomb, total charge flown till 6 second, divide by the time interval is 6 second. So, divide by 6 will give me 3 ampere. So, you can see the instantaneous current is different at different instant. At t is equal to 2 second, current is 4 ampere, right, and up to 5 second it remains 4, and then it decreases, here it decreases. So, current flowing through conductor varies with time, right, but here what we are calculating on an average value for interval 0 to 6 second. What is on an average value of current that must flow through wire, so that in 6 second same amount of charge will pass through the wire. So, with this current 18 coulomb charge passes through the wire, with this current continuously flowing till 6 second, the amount of charge that pass will be 18, right. So, that is the physical significance of average current. Okay. So, I hope this formula is clear. I is equal to dq by dt and I average is equal to delta q by delta t. So, definition of current is clear. Now, let us move to next topic, current density. current density, I want to find out how much is the current per unit area in a region. So, here what is current per unit area, or here what is current per unit area, or at any cross section what is the current per unit area, that is defined as current density. So, now you can see that if I take area this way, then all the charge that is passing through the wire, they will pass through this area, right, and it might be possible that current is not uniformly flowing. So, one possibility is here current density is more and somewhere here current density is less. So, the concentration of charged particle here is more when they are flowing as compared to when they are here or here. So, in this situation you can see that if I calculate the current density, current per unit area here, or current per unit area here, or current per unit area here, I am going to get different values, right. But if I take the whole area and calculate the total current passing, then here I will get the average value of current density. So, what happens that current density, current per unit area is total current divided by area will give you average value. So, this is current density average. Current per unit area is the basic definition, and if I take a bigger area divide by total current, this ratio, then I will get the average value. But if I am interested in finding current density here, only in this part, so what I need to do, I have to take this area very small. So, to reduce this area I can use limit, and the expression will become limit delta S tending to 0 di by ds. So, this whole expression can be written as di by ds. So, delta I by delta S here got converted into di by ds. Okay. Here this area is perpendicular to the current. So, this ds element what we have taken here, that must be perpendicular to the current, and we are defining current density this way. Here current density is a vector quantity whose direction is along the direction of current, right. So, we are defining current density as a vector quantity. So, it is a vector quantity as direction is same as the direction of current. If these are the positive charge, they are moving in this direction, then this is the direction of current, and as you can see I am considering J current density in the direction same as current. Current is a scalar, but the current density is a vector quantity. Now, what is the use? Why we are defining this? If I take cross section exactly perpendicular to the current this way, I am getting a particular current passing through this area. But what if I turn this a bit, keeping the magnitude of the area same, area of this one same, I just rotate it. So, if I take something like this, then this will have area vector perpendicular to its surface. So, this angle will be 90 degree and here this angle is 90 degree. We are defining area as a vector quantity, right. So, for a flat surface you can take area in this direction or area in this direction. So, in Gauss law also we defined area as a vector quantity, here we are defining area vector quantity in the same way, right. So, in this situation ds vector and j vector both are in the same direction, right, and when both are in same direction the current density is di by ds, current density over here will be di by ds. If both are not in same direction and I ask how much is the current flowing, right now if I ask how much is the current flowing, you can directly write di is equal to j ds, but when they are not in same direction, like in this situation ds in this direction and current density in this direction, as you can see that some charged particles are not passing through this area. So, obviously the current it is carrying is somewhat less than the current it carries. If you always write it this way, we are not going to get correct result. So, what we do, we write di is equal to j vector dot ds vector, right. If you integrate this one, then you will get current. So, to calculate current passing through the area, if we know current density, take dot product with surface area vector and integrate, you will get the total current passing through the area. So, the whole thing can be written I is equal to j dot ds. So, if I further rotate this one, if I take area something like this, where this is ds, right, and the current density direction, as I already told you, along the direction of current. So, this is j vector. Now, you can see the angle here is 90 degree. If I ask what is the amount of current that is passing through this area, as you can see that all charged particle will pass parallel to this area, there is no charge crossing this area, there is no current associated with this imaginary area. So, when this angle is 90 degree, there is no flow of current, that is automatically coming in this expression. This can be written di is equal to j vector ds vector cos 90 degree. Cos 90 is 0, so this whole quantity will become 0. So, automatically everything will be taken care if we write that in vector form this way. So, this is the use of defining current density. So, if you have current density in a space and you want to find out how much current will be passing through the given area, you can use this expression, right. So, as I already told you, current density is a vector quantity and its direction is same as the direction of current. Current is a scalar quantity, but current density is a vector quantity, right. So, I hope this whole thing is clear. Now, let us take one simple example so that the whole concept gets clear. So, I have taken one cylinder and I am asking what is the current density. Sorry, what current density is given, I am asking what is the current, find the current through the cylinder. So, we have one cylinder Okay, let this be the axis of cylinder and the radius of cylinder is r, capital R, and this r is the distance from the axis of cylinder that is given. So, somewhere here for this particular point this distance is smaller, right, and current is flowing through cylinder this way. So, if current is flowing through cylinder this way, the current density is along the direction of current. So, this is the direction of current density. So, this is the direction of current density, right, J vector. As you can see that here current density is not uniform, current density varies with distance from axis. For different position current density is different. If I draw one more diagram, I am just drawing the cross section of this to make you understand. This is the cross section and look at this one. For r is equal to 0, j is equal to j naught, r is equal to 0, j is equal to j naught. So, here the density is j naught, and as you go away this r increases. When r is equal to capital R is equal to capital R, here current density will be 0. Small r is equal to capital R, these all will get cancelled out, here current density will be 0, right. Now, as I keep going from here to here, the value of current density is reducing. Similarly, this side also it will be something like this, and on the periphery it will be 0. So, you can see that current density is non-uniformly distributed this way, clear. So, as it is non-uniformly distributed, to calculate current from it you need to integrate, right. So, I hope this diagram is clear. I will erase this diagram now. So, to calculate total current through the cross section, what I can do, I can consider a ring over here this way, okay. First I will try to find out how much is the current flowing through this ring, imaginary ring I have considered over the cross section, how much current is flowing through the ring. So, if we just focus on this ring, situation is something like this. This is the way current will be flowing, and this is the direction of current density, and same is the direction of area vector, flat surface, flat horizontal surface you can see, and area vector for this ring will be this way. So, this is the way we have area vector. I am drawing ds over here, okay. So, I hope situation is clear. Now, it is time to integrate. So, we will integrate this one, right. di is equal to j rho ds, right. This can be written di is equal to mod j mod ds mod j mod ds, right, dot product I can write cos 0. So, cos 0 is 1. So, di is equal to j, the value of j we can substitute from here, j naught 1 minus small r by capital R, and ds, what is area of this ring, if the radius of ring is r, if I cut this one and make it a straight, then it will be something like this. This area I am asking. So periphery is 2 pi r and thickness is dr. So area will be 2 pi r dr. So ds will be this, I can use here. So this one will become 2 pi small r dr, right, and this whole expression we will integrate. Let us see what we are getting. So 2 pi constant, j naught constant, this can be written 2 pi j naught, okay, 2 pi j naught I have taken out, and then inside first term I can see r dr integration minus r square dr divided by capital R integration limit. Limit is for whole cross section I need to integrate this. So for whole cross section if I need to integrate, I need to put limit 0 to capital R, 0 to capital R, 0 to capital R, right. Now I hope this part is clear. This I can remove, this element and all, this is clear, I already used here. So this I will remove. Now look at this one. Here I am getting 2 pi j naught r square by 2, r to the power 1 integration. So capital R square by 2 minus, this is r cube by 3. So capital R cube by 3. And this we need to simplify. Let's see what we are getting. So this one and this one will get cancelled out. Here we have 2 pi j naught in bracket r square by 2 minus r cube by 3. This I can write, sorry, r square, okay. R square by 3. If I simplify, this is 2 pi j naught r square by 6. This is the current flowing through the cylinder. If the density varies according to this one, J is equal to J naught 1 minus small r by capital R, small r by capital R, then the current through this cross section is given by 2 pi j naught r square by 6, okay. I hope this whole thing is clear. Now in the same question, if I ask what is average current density, if I ask what is the average current density, then so first question is find current through cylinder if J is equal to J naught 1 minus R by R. And second question is, B part is, so I hope this one is clear. I will erase. So, one more part, find average current density. Find, okay. Now, how to find out the average value of this one? Average value of current, current at a distance R is given, you want to find out average value. So, how we are defining current density? J average is total current, I like total current, divide by, what is the area of cross section? Pi capital R square. So, total area, and be careful, we are writing J, so this area has to be perpendicular to the current, right. So, this area is perpendicular to current. So, how much is the total current? Current we have just calculated, what we got? So, current we were getting J naught into 2 pi, right, and R square by 6, this was the current we were getting, right. Now, so if I substitute this value over here and divide by area, then I will get on an average current density. So, average current density is total current, that is J naught into 2 pi R square divided by 6 into total area through which this current flows, that is pi capital R square. So, J average will become, pi gets cancelled out, I can see 3. So, J naught 2 by 3 is the average current density. So, I hope this example is completely clear. We discuss about total current, how to find out total current, we discuss how to find out on an average current density, right. So, today we discuss two important concepts, how current is defined, how current density is defined. Now, tomorrow we will talk about drift current, random motion of electron, and we will also see Ohm's law, right. So, I hope you enjoyed today's class.